All right, now let's talk about sinusoids, because sinusoids are one of the most important topics for signal processing. So several hundred years ago, Fourier produced a theorem that says that almost any periodic continuous signal can be represented as a sum of sinusoids, that is, sine and cosine waves. So as a reminder, the blue line here is a sine wave, so at 0 radians or time 0, it's at 0, goes through, and it comes up here and it begins to repeat at this point right here. This is 2 pi radians. So if you think about the unit circle that I discussed in my complex numbers review, we have the unit circle, and as you shift back around, you just repeat. And then here's the cosine is orange, so it starts here, comes down, comes back up here, and just like with the sine wave, at 2 pi radians, it would start to repeat. So continuous time analog signals are typically functions of time. We discussed that in our introduction. And if it happens to be a pure cosine wave, which is most of what we'll look at, then it can be written like this. X of t is equal to a naught plus a1 times cosine of 2 pi ft plus phi. All right? Now before we see what each of these variables here stands for, let me point out that I'm going to use parentheses like this, x of t, to represent a continuous time signal, and I'll use square brackets like this to represent discrete time signals. Some authors do that. Some authors use x of t with parentheses for everything, or they might say x of n but still use parentheses. I just think this makes it a little bit easier to identify what it is you're talking about, so I prefer to do that. So let's look at this signal here. 2 plus 3 times cosine of 8 pi t plus pi over 6. So a naught here is the 2, and it's often referred to as the DC component. So what it is this amplitude here, or the y value, about which the cosine cycles. So notice this is sort of the midpoint here. It cycles back and forth around this line. For many things we'll look at, we'll just have 0 for that value, which means we'll cycle around 0. So if we go back and look at what we had here, whether it be the cosine or the sine, here I used a naught was 0, so we cycle around the x-axis. A1 here is the 3 right here. So that's typically referred to as the peak amplitude, and that is the scaling factor for the cosine. Remember that cosine cycles back and forth between 1 and minus 1 in terms of its values. This makes it, the cosine itself, cycle back and forth between 3 and minus 3. And because we're adding the 2 to it, it shifts up. So it's going 3 above the 2 and 3 below the 2. Now you have to be careful about use of the term amplitude. Here I am talking about a cycling sinusoid. Now there's different definitions of amplitude. Some people would use the term amplitude to be from the 2 up to the 5 here, and would say peak amplitude is from the 0 to here. But I think it's probably a little more common to say peak amplitude is basically your max value above the line you're cycling around. But like I said, different people use different definitions, so you just have to be careful what it is you're discussing. F, from our original equation, is the cyclic frequency. In this case, it's 4, right? And it's the number of cycles per second or hertz. So if we look at here, we know as we come down and we start to repeat right here, so that's 1, 2, 3, 4. This is 1 second. 4 cycles in that 1 second. Now I simplified what I wrote. Instead of writing 2 times pi times 4, I just wrote the 2 times 4 was 8 and wrote it this way. Now sometimes people use what's called the radian frequency instead, where they just take the 2 times pi times f and multiply that together just to get omega here. And finally we have phi is equal to pi over 6 in this case. That's the phase shift. That's shifting the cosine wave left or right. And for every multiple of 2 pi, the cosine shifts back to whatever the current position is. So if this was 0, my cosine would start at the max value. Let's go back to the original plot. It's a little easier to understand, I think. And I'm going to use the sine wave because it's easier for me to see the cycle. So notice here, there's no phase shift. So I start at 0. But as I add a phase shift, which could be positive or negative, I'm going to cause this sine wave, which really would continue infinitely in this direction and infinitely in this direction, but it would cause it to shift left or right, causing it to peak at a different time value. But if you add enough to it, you basically get right back to where you're at, is what I'm saying. So for every 2 pi worth of phase shift, you get back to whatever it is you had. So if I add 2 pi to this, it would look just like this. While we're here, let's talk about something that's not included in this expression, but that is the period of the signal, normally written as capital T, and it's the inverse of the frequency. So since f was 4 in this case, we have that t is equal to 0.25, and what it is, it's the time between the signal repeating. So from here to here, as we can see, is a quarter of a second. And from here to here is a quarter of a second. And here is a quarter of a second. Back to here is a quarter of a second. Because in this case, f was 4. So now let's revisit what we saw on the first slide. We said that Fourier's theorem says that almost any periodic continuous signal can be represented as a sum of sinusoids. So now that we've seen how to represent a sinusoid, let's put that to use. So let's create a program. So here I'm going to import numpy as np, matplotlib as pyplot. Let's create a complicated signal. So here I'm going to say x is equal to np.arange 0, 1, point. So what is this? Well, I'm just producing the x values that I need to ultimately create the plot. And let's combine 3 different sinusoids. So we'll say y1 is equal to 3 plus 2 times or this should be np dot cosine. 2 times np dot pi times, we'll make it a 4 hertz signal with no phase shift. And then y2 is equal to 0. I'm just doing it to make it consistent, but normally I would leave out the 0 in this case. Np dot cosine, and if we want to make it really consistent, I say it's 1 times that. 2 times np dot pi times 5 plus np dot pi divided by 6. And let's say y3 is equal to minus 1 plus 5 times np dot cosine 2 times np dot pi times 7 minus np dot pi divided by 4. And now y is equal to y1 plus y2 plus y3. So what am I doing here? Which of these really is a vector of terms? So because I'm using x here, which I left out, sorry. Good thing I was discussing it. All right. I'm using vectorized operations. So this right here will be 1,000 values. So it goes from 0 to 0.999 in steps of 0.001. And for those 1,000 values, I'm going to produce 1,000 values for y1, where I use x is 0 the first time, and then I use x equals 0.001, then x equals 0.002, and so forth. So there will be a total of 1,000 values there, 1,000 there, 1,000 there. And so this y will consist of the first term of each vector, the second term of each vector, and so forth. And now let's plot it. plt.plot xy. And I'm also going to add some stuff, plt.grid, to make it a little easier to see some stuff. And let's see what happens when I run it. So there's our signal. So what Fourier was telling us is that if I had given you this signal here, that we could have decomposed it into this. This will be 1, right? Because right there, right? So let me line some stuff up, make some of this a little easier to see. And there's no phase shift here. Or actually 4 is what I was using over here. Sorry, I thought I'd left it out, but I hadn't left it out. I put it after the fact. All right. So it's still the same thing. What we see here, we can check that. Say that again, run it again. So what Fourier's theorem tells us is that if this had been our original signal, we could decompose it into a 4 hertz, a 5 hertz, and a 7 hertz set of cosines. Right? And I could have added sines in here if I want to, but I don't need to. Because really, what's the difference between sine and cosine? Well, they're just shifted by pi over 2. So let's go back and look up at the top, our original plot. If I take this right here and move it over to pi over 2, this shift, they look the same. So any cosine can really be represented as a sine with the right phase shift, and any sine can be represented as a cosine with any phase shift. So here's my complicated signal. I have to be careful not to say complex since we do deal with complex numbers. This complicated signal is really made up of these simple signals. 4 hertz, 5 hertz, 7 hertz. All right. That's why we're here. Let's look at some stuff. Say 4, 1, 1. So what I'm going to do is plot each of the individual ones. And so we'll take this right here. So I'm creating subplots so we can see the alignment of each of these. I think I had that right. Let's hope so. So there's my 4 hertz, 5 hertz, 7 hertz sine waves. And we finally get this. We can clean that up a little bit. And see that separated so I can still see the X values. So 1, 2, 3, 4 peaks. About 1, 2, 3, 4, 5. We start over here, so 1, 2, 3, 4, 5, 6, 7. And there's what we got. So hopefully you're starting to better appreciate why sinusoids are important, and it really comes back to Fourier's theorem, which, like I said, was several hundred years old. But obviously they weren't thinking of digital signal processing back then. In fact, he wasn't even thinking of signal processing. He was using it to measure heat transfer, I think. So another lesson there, I guess, is that things you think aren't related to each other can ultimately be related.